Hello, Chemistry 10HH students. This is Mrs. Ottman, and in this video, I'm going to walk through the test number 4 study guide. I was essentially joking when I told you guys I'd show you some nifty keyboard shortcuts, but since I'm here in equation editor, any sort of Greek letter, you can just do backslash the Greek letter and then hit the space bar, and it'll just show it for you. It's pretty nice. All right, so these are all going to be either type 3s or acid. NO3 is nitrate on the polyatomic ion sheet. You will have your polyatomic ion sheet and a periodic table as well as a calculator for your test. So this is nitric acid. This is a type 3, so arsenic pentafluoride. And then I have an acid again, but there's no oxygen here. So this is hydrosulfuric acid. And then I've got HNO2. NO2, I go to my polyatomic ion sheet. That is nitrite, so it becomes nitrous acid. Then I have acetic acid, so I go to my polyatomic ion sheet. I find acetate, and I crisscross it to get HC2, H3O2. For carbon tetraiodide, I get CI4. Iodine monochloride, that's just ICL. And then oxalic acid, I find oxalate on the polyatomic ion sheet. I crisscross it with H+. I don't simplify, just imagine that there's parentheses around the C2O4 with a 1 on the outside, which is why I don't simplify. All right, moving on to the next one. For the purposes of getting this in a video format, I'm going to do what's called an icebox. This is exactly identical to what we did in class, but it just makes it easier to keep track of everything since I'm doing this in a sort of video format, which I'm just more prone to making mistakes when I do things that way. Icebox just stands for initial, change, equilibrium. And for right now, just think of equilibrium as meaning after the reactions. Way more on that later, but for right now, we're going to consider that to just be after the reaction. So for right now, I'm just going to look and see I've got the product mixture. Therefore, that's my equilibrium. So I've got 1, 2, 3, 4 NO2s, and I've got 1, 2, 3, 4 NOs, and I have 0 oxygens. This is just got a placeholder box. So that tells me right away that O2 was my limiting reagent. And so I'm going to use the fact that I produced 4 molecules of NO2 to figure out how much NO2 and O2 that I used. So that tells me I used 4 molecules of NO. I used 2 molecules of O2. I produced 4 molecules of NO2. So that means I had to have started with 8 of the NOs because I used 4 of them. I had to have started with 2 oxygens, and I started with 0 NO2s. So then I just need to draw what I see. So 8 NOs and 2 O2s. This might look a little wonky doing it here, but I'll do my best. All right, I don't know if I'm going to get to make this this way, but just imagine I have 8 of these NOs. And then 2 NO2s. And I didn't even need to put that there. You would draw 8 of those. Since I'm working with the touch screen, it's a little bit wonky, but that's what I'm looking for the answer there. Right, moving on. Right, so when I look at this, I'm seeing I'm only starting with 1 number, which indicates to me that this is not a limiting reagent problem. So I'm looking for the maximum quantity of ethanol in grams. So I'm doing a gram to gram calculation. So first I need to figure out the molar mass of C6H12O6. So I get, oh, that's not right. (180.18 gram mole). And the mole to mole ratio. BTOH is just an abbreviation for ethanol. You could use C2H5OH, and that's equally correct. The ET is for ethyl, and then OH is just alcohol, the functional group. I just have to calculate the molar mass of ethanol. And then I'm going to round that to 4 significant figures. Right, now for B, it's now asking for the maximum volume of ethanol from this reaction. So I just take that same reaction, and then at the end, I'm going to use the density. And then just think to myself, does this answer make sense? And since the density is less than 1, the fact that the volume is a little bit more than the mass, that all checks out. Okay, now on to a sort of word problem. So these could incorporate some of the nomenclature that could include type 1s and type 2s. So I have gaseous carbon monoxide, so that's just CO2 gas. Reacts with oxygen gas, so that is one of our Hankel groups. It takes a subscript of 2, so O2, to form. So that means I need the arrow. And then carbon dioxide gas. Then from here, I need to balance it. I know right away I'm going to need a 2 here and a 2 here. The reason why I knew that was because I knew that the number of oxygens on my left side had to be even. And now I've got 1, 2, 3, 4 oxygens on my left, 4 on my right, 2 carbons, 2 carbons. So this is done. Now I just need to balance it. There's not like a hard and fast way to balance. There's a couple tricks. I'm going to walk through my sort of thought process here, but there's just because I'm doing it one way doesn't necessarily mean it's correct. Or by correct, I mean the best way. It's probably correct. I am a chem teacher. I'm going to put a 2 in front of the H2O because I know I need an even number of oxygens because I've got the 2 in front here. So now I've got a total of 4 oxygens on my right. So I need 4 on my left. So I put a 2 there. Now my hydrogens are balanced. Everything looks good here. So when I look here, notice how the SO4s stay together, sort of like a trick that sometimes helps students. Sometimes students prefer to rewrite water as HOH because I've got the OH here and the OH here. If that doesn't work for you, don't worry about it. But if it works for you, it might be useful. So in short, I need a 2 here and a 2 here. So this, I've got 3 and 2. I need them both to be 6. Right. Another sort of thing with the even numbers, I've got O2 here, so therefore I have to have a 2 there to balance it out. I end up putting a 2 here just to make it work. Okay, NaHCO3. So I know I need to put a 2 here because I've got the Na2, I've got the H2, I've got a couple of things going on. From here, I will need to put my carbons are balanced. I've got 6 oxygens, 3, 4, 5, 6. Yeah, actually, this is balanced. I'm going to make a table for this one because it's one of the ones that's just a little bit more complex. I've got 2 sodiums in my reactants, 2 in my products. Got 2 hydrogens in my reactants, 2 in my products. I've got 2 carbons in my reactants, 1 from here, 1 from here, 2 carbons in my products, 2 times 3, 6 in my reactants, 3 plus 1 plus 2, 6 oxygens in my products. So this is balanced. So now we're given a molar mass, and then we want to know if the molecular formula is one or the other. So all you really need to do for this one is see if the molar mass is set up. So no, I don't even need to really show any work here. So when I put the first one in my calculator, I get 97-ish grams per mole. If I put the second one in my calculator, I get around 194 grams per mole. So I'm just making sure that the molar mass checks out. Okay, for number 8, I actually do need to do a calculation to determine the molecular formula. Right, so right away I see that my carbon and my oxygen are approximately equal, so it's just a matter of figuring out the ratio of hydrogen to carbon and oxygen. So 6.5 over 3.33, that is approximately 2. So this is CH2O for the empirical formula. I wasn't given any other information, so I don't need to solve for molecular formula. So this is one of the sort of older ones that we've done. So we're just going to do like a straight calculation from grams to moles, or molecules rather. Calculated the molar mass of H2O. Rounded to 3 sig figs. Okay, so when I look at this problem, I see that there are 2 numbers going on here. So that means this is a limiting reagent calculation. For both of these, I'm going to be looking for C2Cl2 in grams. And then I have to go through the entire same process with Cl2. Oh, that says 70.9 there. You may have already figured that out. The question did not ask for the limiting reagent. Had it asked for it, the limiting reagent would have been Cl2, but this is the theoretical yield. Because it's the lower of the two numbers, so once I make 2.97 grams of S2Cl2, I'm going to run out of Cl2 and I will have excess S8. So some of these we've discussed similar things in class. The limiting reagent, this is false. The limiting reagent can never be present in excess. I put that star there because when I say never, I'm talking about in experimental cases. If we're talking about single atoms in theoretical cases, there's an argument for that. And I did accept that argument on your lab quiz as a number if you did make that. But as far as labs go, when we're working with grams and orders of magnitudes of atoms, you're never going to have something that's a limiting reagent that is also present in excess. For the second one, I just go to my periodic table. I take a look at the molar mass of lithium. It is 6.941. So that is way closer to the mass of 7. So this is false. This one is more common. This one is true. Try it for yourself. CH2O versus C2H4O2. No matter what, the ratios will be the same. If the ratios are the same, the percent composition will also be the same. This one is false. This would be two chemicals with the same molecular formula. The last question, if we know the empirical formula, what additional piece of information do we need? We need the molar mass. Right. I hope this was helpful to you. If you did find some kind of mistake in it, I did it all in one take, so I could have totally made a mistake. Just please put it as a private comment, and then I will put as a comment on Classroom any mistakes that I find in this. Hope this was helpful. Enjoy your snow day. Have a good weekend. Bye.